So in the previous lecture you were introduced to Gauss's law, which can be written as the electric flux phi E is equal to the integral over a closed surface of E dot dA, and that is equal to Q enclosed divided by epsilon naught. We saw how this could be used to calculate the electric flux through a closed surface if we knew how much charge was enclosed within it. However, this is not all it can be used for. For situations with a lot of symmetry, such as a sphere of charge, an infinite plane of charge, or an infinite line of charge, we can use Gauss's law to work out the electric field. So in order to calculate the electric field for these situations, there's a few steps to follow. So firstly, we should choose a suitable Gaussian surface. So in order to exploit symmetry as much as possible, we want the electric field and dA, the little surface area increments, to be either parallel or perpendicular to each other. Secondly, we need to calculate the total amount of charge enclosed within the surface. So find out what Q enclosed is. And then thirdly, we should use Gauss's law that the integral of E dot dA is equal to Q enclosed on epsilon naught to find E. So in order to learn how to do this, it's most effective to start by watching a worked example and then to work through the process yourself. So let's start by looking at how we can calculate the electric field due to a sphere of charge. So our first example. Consider a non-conducting sphere with a radius capital R and total charge capital Q uniformly distributed through it. Part A, derive an expression for the electric field outside the sphere at a distance little r is greater than big R from the center of the sphere. Part B, derive an expression for the electric field inside the sphere at a distance little r is less than big R from the center of the sphere. Okay, so to do part A, the first thing we have to do is choose a Gaussian surface. So we've got this sphere of charge here. It's got a radius capital R and it's got a total charge Q in there. Now when we're choosing our Gaussian surface, we want to exploit symmetry as much as possible. Ideally, we'd like our surface to be parallel or perpendicular to the electric field. So because this is a sphere, it makes sense to choose a spherical Gaussian surface. So this is our Gaussian surface here with a radius little r. So this is the Gaussian surface. Now, the second thing we had to do was calculate Q enclosed. So this is the total charge enclosed within the Gaussian surface. So the only charge enclosed within the Gaussian surface is the charge of this sphere here. So in this case, we've got that the enclosed charge is equal to Q. And then in step 3, we used Gauss's law, which is that the electric field times the area, the dot product of those, is equal to Q enclosed over epsilon naught. Now, there's several things that we can note about our Gaussian surface and the electric field. Because this is a sphere, we'd expect our electric field lines to be moving out from it like this, evenly distributed. And we also know that dA is out perpendicular to the surface. So this is the direction of dA here. So you can see that dA for the Gaussian surface and the electric field are parallel to each other. So because they're parallel to each other, we can write E dot dA is equal to E dA. So the electric field and dA are parallel. Now, the other thing we can see is because of the symmetry, this Gaussian surface is always the same distance from the center of this sphere here. I haven't drawn it very well, but in reality, that's how it is. So in that case, we would expect that the magnitude of the electric field would be the same at every point on this surface. So we can say the magnitude of E is the same all over the Gaussian surface. So because the electric field here, the magnitude of it is constant, that means we can just pull it out the front of the integral. So we've now got E times dA, and then this is Gauss's law, so that is equal to the enclosed charge over epsilon naught, but we have already worked out what the enclosed charge is in step 2. It's equal to Q, and so this is over epsilon naught. Okay, so all we need to do now to get the electric field is to evaluate what this integral over dA is. The circle, remember, just shows that it's a closed surface. So if we sum up the area, the dAs of each of the little increments over this surface, we're just going to end up with the surface area of the sphere. So we can write this as E times the surface area of a sphere, which is 4 pi r squared, because it's the Gaussian surface, so at radius little r, and that is equal to Q over epsilon naught. And then rearranging this, we end up with our expression for the electric field is given by Q over 4 pi epsilon naught r squared. So if we wanted, remembering that 1 over 4 pi epsilon naught was K, we can write this way. Now, it's worthwhile just making sure that this makes sense given what we've learned about previously. As the radius gets really, really big, we're getting a long way from a sphere of charge. So that sphere of charge starts looking like a point charge. And we know that this is the expression for the electric field from a point charge. So it does make sense. Okay, so part B. To do this, let's just clear some space. Okay, so part B, we work through the same method. So the first thing we want to do is choose a Gaussian surface. So once again, we've got a sphere of charge with a radius capital R, only now we're looking at what happens inside. So our Gaussian surface is going to need to be inside this sphere, and we need to exploit as much symmetry as possible. So once again, we're going to choose a spherical Gaussian surface, and it'll have a radius little r like that. So this is our Gaussian surface for this case. Okay, now the next thing we need to do is find Q enclosed. Now that's a little bit more complicated this time. We're told in the question that the charge is uniformly distributed throughout the sphere. So it'll be useful to consider the volume charge density. So that is equal to the total charge divided by the total volume. And the total charge within this Gaussian sphere is going to be equal to the density times the volume of the Gaussian sphere, which is 4/3 pi little r cubed. So we can substitute in our expression for the volume density here, and we've got Q times 4/3 pi little r cubed divided by 4/3 pi big R cubed. So you can see the 4/3 cancel, and we end up with an expression for our enclosed charge of Q times little r cubed over big R cubed. Now in part 3, we solve Gauss's law. E dot dA is equal to Q enclosed over epsilon naught. Now, once again, we would expect our electric field to be heading out like this, evenly distributed and away from the center of our sphere. And our sphere has dA heading out from its surface and perpendicular to that surface. So you can see DA and E are parallel. So DA and E are parallel. And it's also can be reasonably assumed that the magnitude of the electric field is constant over this surface due to the symmetry. So let's list that here. E is constant over Gaussian due to symmetry. So we can write, well, E dot dA, because they're parallel, we can get rid of the vectors. So that's E dA. And then because the electric field's constant over the surface, we can pull it out the front of our integral. And then integrating over a closed surface, that just gives us the surface area of that closed surface. So we've got E times 4 pi r squared. And then from Gauss's law, we know that this thing is equal to Q enclosed over epsilon naught. And we know that Q enclosed we calculated here. So it's Q little r cubed over epsilon naught times big R cubed. Okay, so what we're trying to do is find the electric field. So we'll want to solve these. So we've got E times 4 pi r squared is equal to Q r cubed over epsilon naught r cubed. And so the r squared there will cancel with 2 of those r's there. And we can write this as E is equal to QR over 4 pi epsilon naught r cubed. So that's our expression for the electric field. Now we should just check that it's sensible. We'd expect that at the very center of the sphere at r equals 0, we would have no electric field, and because of the symmetry, because there's no enclosed charge there, and also we'd expect any contributions on either side to cancel each other out. So this does go to 0 when little r goes to 0. We'd also expect it to become the same as case A when little r equals big R. So right at the edge of the sphere, because the world is nice, we'd expect to have a continuous charge distribution. So if we put in bigger R here, then we do end up with Q times 4 pi epsilon naught on R squared, which is the same as the expression we got for part A. So of course, if we wanted, we could write this as QRK times r cubed, just using that k is equal to 1 over 4 pi epsilon naught. Okay, so that's how we solve it for inside a non-conducting sphere. So in the second example, we're going to consider a conducting sphere with a radius r, which has a total charge plus q. And in part A, we're asked to describe the charge distribution on the sphere. In part B, derive an expression for the electric field inside the sphere. And part C, derive an expression for the electric field outside the sphere. Okay, so we have looked at charge distributions on conductors before, and we've said that the charge is always found on the outside of the conductor. So if we're going to draw a diagram here of our sphere, the charge Q is going to be evenly spread around the outside of the conductor at radius capital R. So the answer to part A is charge goes to the outside of a conductor. We'll say the total charge plus Q is evenly distributed on the sphere at radius R. So now in part B, we're asked to derive an expression for the electric field inside the sphere. So in order to do that, we first of all identify a Gaussian surface. So because it's inside, we choose a Gaussian surface inside, and to exploit the symmetry, we choose a little sphere, and we'll choose this little sphere with radius little r. So this is our Gaussian surface. Now, next we work out the charge enclosed within this Gaussian surface. As the total charge Q is all on the surface of the sphere, there is no charge which is inside this smaller sphere. So we've got Q enclosed is equal to 0. And now we can make use of Gauss's law that the electric field times the surface area. Now in this case, the electric field, we'd expect it to be symmetric, so going out like this. If there is an electric field, it should be going in this direction. And we've got dA, which is going out from our sphere. So these are parallel. So we can write, well, this is equal to EdA as E and dA are parallel. So it's good to give reasons as to why we can make each of the simplifications that we're making. And then we can assume that the electric field is constant over this surface. So because of the symmetry, so that means that we can pull E out the front as E is constant over, well, the magnitude of the electric field is constant over the surface due to symmetry. And so this is equal to E. When we integrate the surface area, we get 4 pi r squared, the total surface area of our Gaussian surface. And then we know that this is equal to Q enclosed over epsilon naught, but Q enclosed we've said is 0, so this is equal to 0. So this tells us that 4 pi r squared E is equal to 0, which tells us that the electric field must be equal to 0. Now, that's not surprising because when we were discussing the charge distribution on a conductor, we said that if the electric field was not 0 inside the conductor, then the charges which are free to move would feel a force and they would move. So we actually expected this result, but we can also prove it with Gauss's law like we've just done. Now in part C, we're asked to derive an electric field outside the sphere. So for this one, we've got our sphere with a charge plus Q around the outside, and we're going to choose a Gaussian surface which is outside. So this will be at radius little r again, where little r is outside the sphere. So this is our Gaussian surface. And then this is very similar to the case for the non-conducting sphere. So the charge enclosed within this Gaussian surface is equal to plus Q. And now we just use Gauss's law like we did up there. We've got E dA. And if we consider the directions, we'd expect the electric field to be going out like this. And dA always points out from our Gaussian surface, so these are parallel. So once again, we can write this as E dA, as E and dA are parallel. And then we can pull E out the front again, as E is constant over the surface due to symmetry. And so this is equal to E times, when we integrate over dA over the entire surface, we just get the surface area. And then this is equal to Q enclosed over epsilon naught, which is Q over epsilon naught. So now we can rearrange this. We've got E times 4 pi r squared is equal to Q over epsilon naught. So this tells us that E is equal to Q over 4 pi epsilon naught r squared, which if we want, we can write as KQ over r squared. So you'll notice this is exactly the same as for the non-conducting sphere. So you'll notice that this is the same as a non-conducting sphere, which isn't actually that surprising. Once we're outside the sphere from the electric field alone, we can't tell if this is a conducting sphere or a non-conducting sphere. And you'll notice that this is actually the same expression as for a point charge. So it doesn't matter if the charge is concentrated in the middle, spread throughout the sphere, or on the edge of the sphere like this. All three of those situations give the same expression for the electric field.